Hi everyone, thank you for your interest in our work. I'm Sajin Koroth from University of Victoria, and this is joint work with Paul Beame at University of Washington. This talk is about lifting theorems, which are a powerful tool in theoretical CS, which has led to breakthrough results in many adjacent areas like game theory, quantum computing, linear programming, etc. In today's talk, we're going to talk about the pursuit of quantitatively improving these lifting theorems so that we can get further breakthroughs in these areas. Lifting theorems, as the name suggests, lift results from a weak model of computation to a strong model of computation. So here is a weak model of computation that's used in standard lifting theorems. It's the model of decision trees. Decision trees are a simple model, but which are powerful enough to capture many revolutionary algorithms in areas like learning algorithms or quantum algorithms. So they are simple but powerful. And in this model, you're allowed to, you don't have the access, you don't have an unhindered access to the inputs, but you can only access the inputs bit by querying them. So here is a decision tree computing the standard OR function, which is 1, OR function on 2 bits, which is 1 if one of the 2 bits is a 1, and it's 0 if both of them are 0. So the decision tree queries variables and then computes the answer once it knows the answer. And a lifting theorem translates lower bounds about a function being computed in such a weak model like decision tree into a powerful model of computation. Usually this is a powerful model of computation is the standard two-party communication complexity model that you may be familiar with. So in this setting, there are two players, Alice and Bob. Each have their own individual inputs x and y. Alice cannot see what Bob has. Alice doesn't know y, so Bob, and similarly Bob doesn't know x. And they want to compute some function, pre-agreed function of their inputs f of xy. And the goal is to communicate as few bits as possible between them to compute the value of xy. And another the strong model of computation that one might consider are decision tree with more complex queries. So here you can consider, here we have the example of parity decision trees. So in parity decision trees, instead of having queries to individual bits, you can have queries to a bunch of inputs, the queries which ask for the parity of a subset of input bits. So for example here, the parity decision tree at the root queries the parity of Z1, Z5 and Z8. So the answer you get just reveals the parity. It doesn't tell you what Z1, Z5 or Z8 is, but it tells you the parity. So this is a more powerful model because trying to figure out the parity in the decision tree model would require you to query both, like to query all Z1, Z5 and Z8. To talk more about lifting theorems, I'd like to introduce an important operation of Boolean functions known as block composition. It is a simple operation. It involves two Boolean functions. Let's say f, which is on n bits, and g, which is on m bits. The block composition of f and g, denoted by f circle g, is a Boolean function which takes nm bits of input and produces 1 bit of output. The precise definition of this block composition will differ to the next slide, but its connection to lifting theorems is as follows. So lifting theorems, as we said, translate lower bounds from a weak model of computation to a strong model of computation. So what it does is that it takes lower bounds about a specific function f in the weak model of computation, let's say decision tree model, and then it would translate it into lower bounds about the block composed function f composed with g in the strong model of computation, let's say communication complexity. And the power of lifting theorems is that, like, once you prove a lifting theorem, it's usually for a specific well-crafted g, but it works for any function f. So once you have a lifting theorem for a specific g, it works with any function f. So you have lower bounds of f, it automatically translates lower bounds for f composed g in the strong model. And this function g which is carefully chosen, is known as the gadget. Okay, so let's talk about block composition in a more detailed manner. So here I'd like to talk about block composition in the setting of communication complexity. So in the setting of communication complexity, the F you have is you want to translate the lower bounds on a standard Boolean function F in the decision model to lower bounds about a two-party function F composed G. But in the so F, let's say, is on n bits and it takes inputs z1 to zn, then we take G to be like a two-party function. So there's a natural partition of G's inputs into Alice's parts and Bob's part. So here, if you look at the first copy of G, it takes x1. So x1 is Alice's input and it takes y1, which is Bob's input. So G is it's a function in the communication setting. F is a function in the standard like decision trees setting. So, and how do you define F composed G? So you take the ith input of F, let's say Zi, and define it to be the output of G applied on Xi and Yi. Okay, so this is the natural definition that I was talking about in the earlier slide. And this is a very natural definition for many reasons. One of the reasons is that like many interesting functions that you want to understand in the setting of communication complexity can be written as a block composition. For example, one of the more prominent functions which are used in many applications of communication complexity is the disjoiners function or its complement, the set intersection function. Here Alice and Bob are given characteristic vectors of two sets and they want to know if their sets have an intersection. This can be naturally written as the block composition of the standard OR function on n bits with the AND function on 2 bits in the following sense. So Alice has inputs x1 to xn and Bob has inputs y1 to yn, and xi is 1 if Alice's set has this element I, and yi is 1 if Bob's set has the element I. So their sets intersect if there's some index I in n where xi and yi are both 1. So this AND, so if they do intersect, one of these ANDs would turn on, and when the output of an AND is 1, the output of the OR naturally becomes 1. So this naturally computes the set intersection function. So just to recall, many interesting functions can be written as natural block compositions. So to summarize, lifting theorems are theorems which work for a specific gadget G and for all functions F, which essentially say that the communication complexity of the block composed function F composed G is approximately equal to the decision tree complexity of F. And if we are considering the lifting from query complexity to two-party communication complexity. And the holy grail here is to get gadgets which are as small as possible. Ideally, we'd like to get gadgets which are just constant size. And lifting theorems have been instrumental in solving long-standing open problems in many areas like combinatorial optimization, communication complexity, proof complexity, circuit complexity, game theory, etc. So in this slide, I want to talk about frontiers of lifting theorems. So the main overhead in lifting theorems is the gadget size. So recall that lifting theorems transfer lower bounds for a function f on n bits to a function f composed G on n m bits. So ideally, we want to keep the m of the gadget as small as possible. And the holy grail in this direction is to get m constant. But even getting m to be substantially smaller than what is known would result in breakthrough results in circuit complexity, proof complexity, etc. And these are on problems which have been open for a very long time, and they're really hard problems. So here's a quick overview of our results. So our first result shows that currently known techniques cannot reduce gadget size to to constant for general lifting theorems. We actually prove something stronger. We show that even going beyond below log n is not possible with current techniques for general lifting theorems. Nonetheless, we show that if you want to prove lifting theorems which lift decision tree complexity to somewhat stronger models, maybe not something as strong as two-party communication complexity, but a stronger model like parity decision trees, you can get a lifting theorem with a constant size gadget. We prove a lifting theorem with constant size gadgets from simple decision tree complexity to parity decision tree complexity. We show that decision tree depth can be lifted to parity decision tree depth. And similarly, decision tree size can be lifted to parity decision tree size. And this result, this lifting theorem, has interesting consequences in proof complexity. Using this result, we actually show that tree resolution proof size can be lifted to tree res parity proof size. We'll talk in detail about what these proof systems are in the later slides. So what do we mean by current techniques? So we use this to refer to simulation-based approaches for proving lifting theorems. So what are simulation-based approaches to proving lifting theorems? So usually in a simulation-based approach, a query to communication lifting theorem is proved in two steps. The first step is the easy direction, and the second step is the harder direction, which is known as the simulation theorem. So in the first step, it shows that the communication complexity of the lifted function f composed G is upper bounded by the decision tree complexity of f times the communication complexity of G. This essentially says that if you have a efficient decision tree computing f, you can turn that into an efficient communication protocol computing f composed G. The idea is fairly straightforward. So Alice and Bob want to simulate the decision tree computing f to come up with a communication protocol computing f composed G. So here, let's say this is the decision tree computing f. It queries the variable z1, but Alice and Bob has no clue about the value of z1. So they need to know the query answer to z1 to proceed along this decision tree. But they know that z1 is the result of applying the two-party function g on x1 and y1. x1 is Alice's first input and y1 is Bob's first input. So they can compute the value of g of x1, y1 using the best protocol for communication protocol for g, using just cc of g bits. So by just exchanging cc of g bits, they can figure out the value of z1. And based on the value of z1, let's say it's 0, they continue the simulation and go down to the next node in the decision tree, and then at c2, they don't know what is the value of c2, but they know that z2 is g applied to x2, y2, so they similarly run the protocol for g again, so on and so forth until they come to an answer. And the cost of doing the simulation is just the decision tree complexity of f, which is the number of queries you make on the path, times the communication complexity of g. So this is the easy direction. So in the hard direction, what you want to say is in the reverse direction. Suppose you have an efficient protocol, communication protocol solving f composed g, then you want to use that to come up with a decision tree computing f, whose query complexity is related to the communication complexity of f composed g divided by cc of g. So this is usually done by designing a meta-algorithmic recipe, which takes an arbitrary protocol that solves f composed G, which is somewhat efficient, and uses that to come up with a decision tree computing f. So the simulation, the high-level idea behind the simulation is as follows. So we start with a protocol pi solving f composed G given on the left, and we use that to come up with design a decision tree for f on the right. So we start at the root of the protocol. Initially, at the root of the protocol, the players haven't spoken anything, so they don't know anything about any of their inputs. But after communicating for a few rounds, Alice and Bob might learn a good amount of information about some of their inputs. Let's say in this point, we are in the simulation, and in the simulation, we're going to trace a path from root to one of the leaves. And let's say we are at a node where Alice and Bob has learned quite a lot about x3 and y3. But it's not all the information, but they've learned just enough information. At that point, in the simulation theorem, we would query the variable c3. So before they learn enough information about x3 and y3 to decide what is the value of c3, we would just query z3 at this important threshold. And based on the query answer that we get, we'll continue the simulation until and unless some other set of variables become revealed in terms of amount of information Alice and Bob has learned. At that point, we query that variable, we continue the simulation until we get to a leaf node of the protocol. And at the leaf node of the protocol, the players know the value of f composed G, and looking at that value, we can decide the value of f for the decision tree. So this is the high-level idea behind simulation. To carry out such a simulation, we need to maintain a set of invariants. So at any point, and so what are we doing in the simulation? We are trying to trace a path from root to one of the leaves so as to compute the value of f consistent with the query answers that we have gotten so far, right? So at any point in the simulation, we maintain a set of inputs of Alice and Bob, denoted here by the set curly x and set curly y. And we want to maintain some invariants for this set of inputs. So the first is a very natural invariant. We call it the fixed coordinate invariant, which is that so far in the simulation we have queried a bunch of input variables, let's say z1, z2, and z5. So we want to make sure that the set of inputs that we are currently keeping track are consistent with the query answer that we have gotten so far. So here we denote I to denote the already queried coordinates, and we want to ensure this consistency constraint that if you look at the set of inputs that we are maintaining and you look at the gadget output on those coordinates I which have been queried, the value of the gadget is consistent with the query answer. The other property, known as the disperser property, is the more important one, and this ensures that for the remaining coordinates which are unqueried at this point, the players do not know anything on whether zi is 1 or 0. So for the remaining coordinates, we have to maintain all possible future query answers. So we want to say that this set of inputs x and y are so rich so that if you look at the gadget output on the remaining unqueried coordinates, they give you all possible 0, 1 strings of that length. And to maintain this invariance, especially to maintain the disperser property, we need to do some bookkeeping. So as we go along in the simulation, we'll add new coordinates to this queried coordinates and do some cleaning up to make sure that everything is nice and tidy. Just a quick note here that if you are proving lifting theorems for randomized in the setting of randomized algorithms, you need a stronger property known as the extractor property instead of the disperser property. But here we are focusing on deterministic lifting theorems. So let me tell you a bit about what these nice measures that we were talking about in the last slide, which ensure that the gadget has the disperser property. So historically, the first nice measures that was used to ensure disperser property for the index gadget was the average degree. It's used in the original paper of Ras and McKenzie, who proved a lifting theorem and as a consequence got the separation of the monotone NC hierarchy. But it was already known that this approach based on average degree can only give you linear sized index gadgets. The other two measures, which are usually used in combination, are the information theoretic measures of mean entropy and deficiency. So the disperser property is also a function of the gadget and not just the nice properties, nice structures, nice measures. So we introduce the two gadgets which are very commonly used in lifting theorems. So one is the index gadget and the other is the inner product gadget. Index gadget is a gadget where Alice gets a pointer, which is a value in 1 to m, and Bob gets a memory bank of m locations, which we think of as a binary string in 0, 1 to the m. And the output of the index gadget at x, y is just the value y has at location x. So whatever Alice is pointing to in Bob's input is the value of the output of the index gadget. And the communication complexity of the index gadget is log m. Similarly, another very popular gadget is the inner product gadget. So Alice and Bob get two b-bit strings x and y, and the output of the gadget is just simply the inner product of x and y over f2. And the communication complexity of the gadget is exactly equals to its input length. Another interesting thing about index gadget is that it's a universal gadget. So if you think of y as a truth table of a log m bits function, then you can encode any function as a specific index of x and y, where y is said to be the truth table of that function. So let's revisit nice measures with respect to index and inner product gadgets. We already mentioned that average degree cannot give you lifting theorems for in index with less than linear size gadgets. But for min entropy and deficiency, the current best gadget sizes are as follows. So for index, we can already get M to be something close to linear, something like n log n. So this was in the paper of LMMPZ in ITCS last year. And for inner product, it's an older result from CKLM from CCC 2019. And for inner product, it's around theta of log n. And for index, it's almost linear. And even reducing the gadget size for index from almost linear to polylogarithmic would lead to breakthrough results. And these are this would be breakthrough results in circuit complexity and proof complexity for really big open problems. Okay, so towards this goal of reducing the gadget size and how the current techniques fare, like Lovett, Meka, Mertz, Vitazi, Zhang in their paper in ITCS 22 made the following conjecture about the disperser property of index. They conjectured that there exists for sufficiently large M for every x and y, which has deficiency very small, at most some delta. They conjectured that this index is a good disperser in the sense that it index on such inputs x and y would contain a subcube of codimension C delta. So there's some set of coordinates I, which is at most C delta in size, which if you exclude them, the index produces every possible binary string. So this is what it means. Is say that index contains subcube of codimension C delta. And this is the disperser property of the index gadget. So our first result proves that this disperser conjecture for index M is false as long as M is less than log n minus omega 1. And it also fails for inner product gadget for the same kind of range. So as long as you have an inner product gadget of size b, where b is less than log n minus omega n, this disperser property is no longer true. So this shows that the lifting theorems for inner product gadgets using current techniques is tight in terms of the gadget size parameter. So because we already know lifting theorems for inner product with the theta of log n size gadgets, and our results prove that current techniques cannot improve it beyond that, asymptotically beyond that. Okay. We also, going beyond, we also prove a deterministic lifting theorem for the index gadget with constant size, despite proving that the current techniques cannot improve it even to sub-logarithmic. But we achieved this by proving lifting theorems for a weaker class of protocols known as semi-structured protocols. So what is semi-structured protocols? These are protocols where Bob can only communicate parities of his input. Okay. So given a Boolean function f, so using this lifting theorem, we prove the following result. Given a Boolean function f on n bits, we come up with a composed function f dash by composing f with an index gadget on constant size, and prove that the decision tree complexity, parity decision tree complexity of f is tight in terms of the decision tree complexity of f, and this decision tree complexity can be either the decision tree depth, which is dt of f, denoted by dt of f, or it could be decision tree size, which is denoted by size t. Independent work by Chattopadhyay, Mande, Sanyal, Sharif also proves the same results on parity decision trees, and you can listen to the next talk to know more about their results. Okay, so using this lifting theorem, we get the following consequences in proof complexity. So we consider a class of proof systems known as res parity proofs. They're also known as res lent proofs. It was introduced by Itzkion and Sokolov in 2014, and they proved lower bounds in 2020. So in a res parity proof, each line in the proof is a affine subspace of the space f2 to the n, and the inference rule just says that if you have a and b, you can derive c if c is a subset of a union b. So if a and b are affine subspaces and c is another affine subspace, and the goal is to derive f2 to the n. Using our lifting theorem for semi-structured protocols, we actually show that tree rest size for a formula phi can be lifted to tree rest parity size for a formula phi dash, where phi dash is obtained by composing this unsatisfiable case in a formula phi with an index gadget of constant size. I'd like to conclude the talk with a few future directions. So our results essentially show that nice distributions and our min entropy rate, simple information, which is like min entropy rate, is not the way forward if you want to improve gadget size using the existing simulation framework. So in the counterexample that we construct, it has this very peculiar structure that a few blocks of Bob's inputs have only zeros or only ones. So one way to avoid such maybe pathological counterexamples would be to consider inputs where every block of Bob has an equal number of zeros and ones. And once you have such a set of inputs, once you restrict, once you maintain such a set of inputs in your simulation theorem, our counterexample no longer works, and we don't know how to disprove the conjecture with such set of inputs. The other avenue is that, okay, so currently there's this gap between the known limitations of there's this Goldilocks zone where you might be able to prove interesting results, where there are no known limitations for current techniques, which is the range of m between n, which is almost linear, to n log n. So can you prove a lifting theorem with m equal to theta? And that's an interesting open problem. And the other thing is that a lot of these improvements and recent improvements in index gadget size came from connection to sunflowers. So can we utilize this connection further to say maybe something about impossibility of improving the gadget size or improving it further? And in this paper, we proved constant lifting theorem with constant size gadgets for tree-like protocols, but there's this other notion of tag-like protocols where it has more applications in proof complexity, and maybe you can prove tag-like lifting for restricted protocols. That's another interesting venue. The other option to consider is that here we considered semi-structured protocols where it was limited in the sense that Bob could only send parities. So instead of parities, you could consider other functions which are limited, like majority or other threshold functions, and we do not know anything in this regime. And this might have by considering an appropriate restricted function family like thresholds to functions or majorities, you'd be able to get interesting results in proof complexity. Okay, that's the end of the talk. Thank you everyone, and if you have any questions or comments, please feel free to email either of us at skoroth@uvic.ca, at beame@cs.washington.edu. Thank you.